In this video, we are going to go over section 3.6, which is related rates. The goal of this section is to solve problems that involve related rates. So, all the way up till this point, we learn how to take the derivative respect to two variables. We call that implicit differentiation. That was section 3.5. So we are given an equation with x and y, just like number one right over here. Now, on top of that, we are going to let one more variable called t, which is we normally associate the t with the time unit. So in this situation in 3.6, we are going to look at situation where there are two quantities and looking at the changes with respect to the time. So third variable. So let me note. So in other words, we are going to look at two quantities that are changing with respect to time, normally associated with the variable t. So the procedure is used to solve related problems like number 2, number 3, number 4, number 5 when we work on word problems. So I'm not going to read through this because it's already written there. But once we go to the actual problem, I'm going to kind of use this procedure by checking off. Okay. Number 1 is like a warm-up problem. This is the easy one because they already give you the function. Starting number 2, we have to come up with our own function. So take a look at this. We have this function, implicit function, because both x and y is on the same side of the variable. 3x squared plus 9x minus 2y cubed equal 15. Now they look pretty much same as last section, except my x function really is a function written in terms of t. My y function also is written as function of t. So we are having, in a sense, three variables to consider. These x functions are really a function written in respect to t. Same thing with y. We have a function that is respect to t. So now it's very important because we have so many different functions. Whenever you differentiate, we have to make a note that we are taking the derivative respect to t function. So that's what we are going to use. dy dt is used when we take the derivative of a y and then respect to t, and then we are going to attach the function dx dt whenever we took the derivative of x function. So let's take a look at number 1. Number 1, the first term, term by term. This is an easy one, and there's only one variable involved, 3x squared. So we do the very basic rule, power rule. Bring down the 2, subtract by 1. So I have 6x. We are not going to stop here. We are finished taking the derivative of x respect to t, because technically our x function is written in t, so that's how you notate. 9xy, you have a two variable, that's a product rule, 9x times y. So recall the product rule, we kind of take the derivative of each product kind of and then rotates with the plus between. So 9x, derivative of y is just 1. In other words, dy dt, plus the second part is y. Now it's alone, and then derivative of 9x is just 9, but dx dt. Don't forget dx dt because we took the derivative of x respect to t function. Minus 2y, that's a negative 6y squared. We took the derivatives of variable y, so we attach dy dt. Derivative of 15 constant is a 0. So that's the first step. Okay. What is the problem asking you to solve? dy dt. I'm looking for dy dt. So I have to solve for this variable. So we are going to move all these remaining term with the dx dt to the other side and then solve for dy dt. Okay, so I'm going to move this one first term 6x. Before we actually do that, let's substitute it to make it simple because we are given these extra information. When we substitute it, the function looks a lot less complicated because it's a number. So let's substitute it. dx dt, x is a 2, so it looks like 6 times 2. dx dt is given as 4. So that will be the first one. Plus 9x will be 2. X is 2. dy dt, I don't know. That's what I'm trying to solve. Plus y is 1. So 1 times 9 times dx dt is 4. Minus 6, 1 square dy dt equals 0. Let's keep going. The first term, 6 times 2 times 4 is 48. Plus 18 dy dt. 9 times 4 times 1 give you 36 minus 6 dy dt. Let's combine 48 and 36. So that's gonna give me 84. And then same thing, I can combine this. 18 subtract 6 will give you 12. 12 dy dt. We are solving for dy dt, so I'm going to subtract 84. So negative 12 dy dt equals negative 48 divided by negative 12. So dy dt, I'm getting the final answer of 84 divided by 12, 7. That's it. Okay, so it's nothing so much different. You still take the derivative, but you just have to attach dx dt after you take derivative of variable function x, and then you also have to attach dy dt term after you took the derivative of y respect to t. Okay, now let's jump on the more main problem where you have application problem. You have to come up with an equation and then take the derivative and then find the rates that they are asking. So let's take a look at number 2. Number 2 says a boat is being pulled towards a dock by a rope. If the rope is being pulled at 5 feet per second and the rope is 3 feet above the dock, how far is the distance between the dock and the boat decreasing when it is 30 feet from the dock? So they're asking two things. How fast, so that's the rate. How fast the distance between the dock and the boat decreasing when 30 feet from the ground. So we are looking for speed, rates. Okay, so I drew a quick sketch. So you have a boat right over here, and then here's the dock, and then this is how much the boat is away from the dock, and then this is a rope being pulled, right? So the boat will go in this direction. So eventually, as the rope gets pulled, this distance will become decreasing, decreasing, decreasing. Okay, so that's the keyword. If rope is being pulled at 5 feet per second, okay, really the distance is getting smaller, so I'm going to use unit negative. But let's start labeling and then start coming up with the equation. So I'm going to since you can see that it's kind of creating the triangle. So let's label the 3 sides. I'm going to let let me label it. A will be the rope height from the dock. So in this case, this will be your A, which is 3 feet already given. Let B be the distance between the boat and the dock. And let C be the rope length. Okay, the rope length. So we have this situation A, this part over here will be B, and this one rope length will be C. Okay, now what are we given? So all this information, we have this 5 feet per second, and then we have 3 feet, which I already have it here, and then we have this 30 feet from, okay? So I have A given as 3. B, do I know B? This part will be B. The boat distance 30 feet from the dock. So B is equal to 30. C, I don't know the rope length. It's not given. But C, we can find this. Recall this one. This is a triangle. Right triangle, Pythagorean theorem. We have 3, 30, C. So we can set up a Pythagorean theorem to solve for C. Let's go ahead and do that. Because we need to know all those unknown values. So quickly setting up 30 square A square plus B square equals C square. So I have 900 plus 9 equals C square. So we have 909 equals C square. So square root C is equal to approximately, I'll round it to the 3 decimal place, 30.150. 30.150. Okay, but the problem is not asking you to find the length of a rope. It's asking you how fast the distance between dock and the boat is decreasing. So the question is this part over here, the speed between the dock and the boat. So I am looking for dB dt. Distance of B respect to time, t, how much feet per second. So I have, this means I want to know dB dt. That's what I'm trying to solve. Okay. What else do I know? I know this 5 feet per second. So rope is pulled, so this has to do with the variable C. So I have dC dt as 5 feet. Now, however, you have to be careful. Now you are pulling, so this distance gets smaller. So I'm not having a positive, I'm having decreasing, negative. Okay. dB dt is the one that we want to find out. What about dA dt? What happens to this? Well, this height, right? The rope on the dock doesn't matter. If I keep pulling this one here, I know both will start going in this direction. However, this height does not change. So dA dt is actually 0. Okay. So these are something that you have to kind of use common sense to come up with these. Okay. So it's very important that you have these related rate value come up with on your own, even though the problem with the explanation of what the problem is given. So let's set it up. Still, I can use that A square. That will be my general formula to show the relationship between all three. Now let's use implicit differentiation to solve. So derivative of A squared is 2A, except we attach the A dt because we took the derivative of function A respect to t. derivative of b squared is 2b, but again, we took the derivative of b respect to time t. C squared is 2c dc dt. Right, now let's start fill in all those variables. A, as I color coded, A was 3 feet, so that's my A. B is 30, that you can see over here, 30. And then C is right over here. Oops, let's use orange. Rope right over here. So 2 times A, 3, dA dt is 0. 2b, b was 30, dB dt is the one that we want to find. The speed, how fast. 2c is the rope length. We found that c was 30.150. dc dt -5 because it's getting shorter. This is just 0. This is 60 dB dt. On the right hand side, I have 2 times -5 times 30.150. So I have, let's see, 10 times 30.15. So that's negative 301.5 divided by 60, divided by 60, so dB dt end up being negative 5.025. Okay, so that means you can see that negative means decreasing. So this is how you write a sentence. Therefore, the boat distance is decreasing. So that's what this negative means. Decreasing. Of what rate? By approximately 5.025 feet per second. Okay? So that was the very first problem. Second application problem is very similar, another Pythagorean theorem. So let's start reading the number 3. A 30-foot ladder is placed against the vertical wall. So there's a diagram kind of given to you. Suppose that the top of the ladder slide down. You see the arrow going down. So you see that it's gonna go down. So I'm going to be using a negative notation with this. So even though it says constant rate, I'm gonna have my A, if this is considered height, my dA dt, you can see that will be -3. Okay. I'm gonna highlight it so that we don't get confused. How fast is the bottom of the ladder sliding away from the wall? So think about this. You kind of have to, on this one, you have to use a lot of common sense. If you push down this ladder, smaller, what happens is this is gonna get bigger. B will get bigger, so it's gonna increase. And I wanna know that rate. So my question is dB dt. How fast is the bottom of the ladder? We use B for the bottom of the ladder length. And then we have a dC dt. So let's keep going. Sliding away from the wall when top of the ladder is 15 feet above the ground. So we have 15 feet above the ground. So that's actually letter A given. Okay. Now what is dCdt? That's the rate of my letter, but letter is stationary. The letter's length will not increase, decrease. When it's 30 feet letter, it's gonna stay. So the speed will be just 0. It's not gonna change in terms of length. Okay. So same thing, it looks very similar. We're gonna set up an equation and you can see Pythagorean theorem. So another a squared, b squared, c squared. Implicit differentiation, substitute the value and solve. That's what this one over here is. We sketch the figure, identify relevant variable, including those that are rates given. So the rates are all those dt terms. That's what we did. Express all the given rates founded in derivative. Find the equation connecting to the variable identified step 2. In this case, the variable that we know is the Pythagorean theorem. A squared plus b squared equals c squared. Implicit differentiate. So let's implicit differentiate the function. That's step 5. So derivative of a squared is 2a dA dt, 2b dB dt, and then 2c dB dt. A is given as 30. dA dt is -3. Now B, we don't know B, but let's do some side work. If this is 15 and this is 30, I can set up Pythagorean theorem and solve for the missing side. So let's do that. So a squared 15 squared plus b squared equals 30 squared. 15 squared is equal to 225. B squared 30 squared is 900. Subtract 225. I have b squared as 900 minus 225, which is 675. Square root b is about 25.98. Just round it to the 2 decimal place. So that's what b is. So that's what this one over here is. Right over here, right over here. So let's replace it. 2 times 25.98. dB dt is the one that we want to find. 2 times c is 30. That's given. This should be dc dt. dc dt is 0. So on the right hand side, we are just going to have a 0. So let's do a little bit of a math here. 2 times 30 times -3 will be negative. Oh, I'm sorry, I made a mistake. When I plug it in A, it should be 15, not 30. 15 here. So 2 times 15 times -3 will give me -90. 2 times 25.98 will give me 51.96 dB dt, and then 0. Okay. Add 90, 51.96 dB dt equal 90. Divided by 51.96, 51.96 dB dt equals to 1.73. So that's the rate. So that's how much the bottom of the letter is sliding away from the wall. 1.73 feet per second. So every second, 1.73 feet, you're gaining that much length. The bottom of the ladder is sliding away from the wall at approximately 1.73 feet per second. Okay. Moving on to number 4, a slightly different example than the Pythagorean theorem. So let's take a look at this. This is another geometry type of problem. The radius of a spherical balloon is increasing at a constant rate of 5 inches per minute. How fast is the volume changing when the radius is 15 inches? So we have a ball, right? And then the radius is increasing. So your ball is getting bigger, bigger, bigger. Maybe like you start blowing the air and then the ball gets bigger, bigger, bigger at a rate of 5 inches per minute. So every minute it's gaining 5 inches. How fast is the volume change? Now this is the main part, the volume. So here, you can just draw the circle of a ball getting bigger. And now this is find an equation connecting the variable. The equation that connects all this is the volume of a ball. So recall the volume of spherical ball is a 4/3 pi r cube. That's something that you have to kind of know. Kind of like area of a circle is pi r squared. So volume of a spherical ball is 4/3 pi r cube. You have probably seen this formula before. So now let's take the derivative, okay? And then start substituting the variable. So again, everything respect to time per minute. So derivative of v is just 1, but dv dt. You know that this is just all constants, so we bring down the power, subtract 1. So if I bring down the 3 with this one, the 3 cancel out. So I have 4 pi r squared dr dt. Okay, we took the derivative of variable r respect to t. Now let's go back and start substituting the value. So we have constant rate. So this is the first part, constant rate 5 inches per minute, increasing. So that is what? dr dt. The radius is increasing at a rate of 5 feet per second. So that's dr dt. That's 5. Increasing, so I use positive this time. Decreasing, I will use a negative value. What else? Radius is 15. So they're given actual radius 15. And that's it. We want to know how fast volume changes, so let's find out dv dt. Okay, so dv dt is equal to 4 pi 15 squared. Dr dt is 5. So we just have to put everything into a calculator. So that is, you can use pi as a 3.14. Final answer, I get 14,137. Okay, so therefore the volume of the balloon is increasing approximately 14,137 cubic inches. Why cubic inches? Volume is unit cube per minute. Okay. All right, one last example, and that's the end of section 3.6. Number 5. A retail store estimates that weekly sale S and weekly advertising cost X, both in dollars, are related by a function S equals 60,000 minus 50,000 e raised to the negative 0.0004x. Well, this is nice. They give you a equation already. So that's good. I don't need to come up with my own. So I'm going to copy that. The current weekly advertising costs are $2,500, and these costs are increasing at a rate of $240 per week. So we have two things given. Current average weekly cost and the rate. Okay. Find the current rate of a change of a sale. So we have a variable X and then S. So we are gonna have we are going to take the derivative, and then we have the S dt and then the X dt, because we have two different variables. So the S dt is the question that we want to find, current rate of change. So that's the question that we need to find out. The X dt is given, that's a rate, 240. And then X will be 2,500, the value, cost. Okay. Weekly advertising cost X, so current weekly advertising, so that's your X value. This is X rate, so the X dt, and then the S dt is one that we want to find. So let's take the derivative. Single variable S, if you take the derivative, that's 1, so that's just the S dt. Derivative of a constant is just 0. Now this one requires a, remember, derivative of EU is equal to EU du, right? So because it's not just the X, so we have negative 50,000. Derivative of this part over here is negative 0.0004. E raise it to negative 0.0004x. Now we took the derivative, so that is dx dt. Don't forget this one. Okay. Let's plug it in. dx dt, I know that. That's given here. X, I also know, so I'm going to substitute that. So ds dt equals 0 minus 50,000 times negative 0.0004. E raise it to negative 0.000 times 2,500 times 240. So let's pull out the calculator. If I multiply these two, I'm gonna have a positive 50,000 times 0.0004, because both are negative. So I have 20. E raise it to negative 0.0004 times 2,500. That's a negative 1. 240. 240 times 20 makes these two 4,800 e to the negative 1. So putting in the calculator, I get final answer. I rounded to the whole number, 1766. So rounding to the whole number. So I'm going to have the final, the current rate of change of sale is $1,766 per week. Okay? All right, that's it for section 3.6. On next video, we are going to be finishing up the last section of chapter 3, which is 3.7.